All right, well, we only got a few of you here, not enough yet, but I guess we need to go ahead and get started. So we're in chapter 10. Last time we had gotten up to torque, and I'd given you a couple of examples, but one of the big things that you're learning in chapter 10 is you're learning how to do a cross product, and I showed you two ways of doing that last time. I'm going to show you a third way today, but I'm also going to show you some more practical ways where, in the event that you don't have, three component vectors for the lever arm and for the force, then you obviously would like to figure out some way to calculate the torque, anyways. So there's some nice formulas for that as well. I'm going to go ahead and open up and share my iPad with you guys, and we'll get started that way. Anybody have any questions before we get started? Okay. So what I have here is a Greek letter gamma. So you might imagine that this is like one of the letters on a fraternity house or something like that. But the main thing is right here at the lower left-hand corner of the letter, we have a pivot point. So the pivot point in principle is just the a dot through which the axis of rotation goes. So the axis of rotation would of course be perpendicular to the page in this case, and what we're saying is that's the pivot point. And in order for you to understand the formulas that I have written, you can see up here I have torque is equal to R cross F. Oops, I just realized that is missing a vector symbol. And then I also have that the magnitude of the torque is equal to R times F times sine theta, which is just another way of stating the magnitude of the cross product, which is the magnitude of the first one times the magnitude of the second one times the sine of the angle between them. Remember how that differs from the dot product, or what we call the scalar product. That one was the magnitude of the first one times the magnitude of the second one times the cosine of the angle between them when they're tail to tail. So this one still has to have the two vectors tail to tail, but it's a sine function between them. And in fact, that actually gives you the area of the parallelogram created by the two vectors R and F. The R vector is what we call a lever arm vector, and the F is a force vector. Now, some other neat formulas regarding the magnitude of the torque is equal to the component of the lever arm that's perpendicular to the force, and it's also times the force, by the way. It's also equal to the component of the force perpendicular to the lever arm times the lever arm. So those are really nice formulas to use as well. So I thought I'd show you in this example here exactly what the lever arm is and then show you how to do calculations. So the lever arm is always a vector that goes from the axis of rotation, i.e. the pivot point, to the point of application of the force. So for this particular force, the 25 Newton one, the lever arm is this vector right here. So that's your lever arm vector for that particular force. For the 30 Newton force, the lever arm vector is that. And for the 57 Newton force, the lever arm vector is that. So you see, that's what the lever arm vector is. Now that you have that in your mind, you can more easily make use of the formulas that I have here. Torque is equal to the component of the lever arm perpendicular to the force times the force, or the torque is equal to the component of the force perpendicular to the lever arm times the lever arm. And when I say times the lever arm or times the force, what I mean is times the magnitude of the force or times the magnitude of the lever arm. So we can tell, for instance, the lever arm for the 25 Newton force. I'll do it like this. Let's go ahead and kill this. I'm going to write solution in red. Torque is equal to R cross F. And I'm going to say torque is equal to RF sine theta, which equals R perpendicular times F, which equals F perpendicular times R. I should say that this actually includes a diagram. So this, for instance, could be the R vector, and this could be the F vector. Notice they're tail to tail. Then you could say that this angle, since they're tail to tail, this angle is the theta. And I think you can see from that, if you imagine completing a right triangle right here, you can see that r times the sine of theta just gives the component of r that's perpendicular to f. So that's why I say r perpendicular to f. You could also create a right triangle right here, and then you'd see with that right triangle, f sine theta is the component of f perpendicular to the lever arm. So that's where that one comes in. And if you remember your theorems from calculus, you can complete a parallelogram like this, say, and the area of that parallelogram is the length of the base times the perpendicular height. So you can see again, r sine theta gives us the perpendicular height of the parallelogram. So in fact, RF sine theta is the area of the parallelogram. So I mentioned all that stuff last time, but it might have hit you kind of quickly because we were doing all that stuff with the determinant and the matrix and all that good stuff. So just that was just a chance to reiterate what torque is in terms of the various ways you can interpret the formulas. It should make some sense to you if you think in terms of riding a bicycle. So here's your what we call your sprocket on your bike that you use to pedal, of course. Okay. And when you think about it that way, you probably can say, well, if the crank is really, really long, then I could really force my bike to take off. So that tells me torque is proportional to the lever arm. Okay, torque proportional to the lever arm. And that's because, again, we think that would be less strong than this. In other words, if I have this long lever arm, I can do a lot of torque, whereas if I have this short lever arm, I can't apply as much torque. So that's why torque is proportional to the lever arm. Additionally, if you put a little force on it or a big force on it, you can probably say, oh, well, the big force would cause a bigger torque, and that's correct too. So you'd reach the conclusion that torque is proportional to the force, and that's right as well. The only thing you're missing though is that if we apply the force at this direction or this direction or this direction, you get very different results. The main reason being that if it's this direction, you've got this component that tends to rotate, but this component down here tends to do nothing. So that's another way of looking at it. Now that we have all that, and now that I've discussed all that, let's go ahead and calculate the individual torques here. So what I'm going to say is 25.0 Newton force. So first off, I want to figure out what the lever arm is. And strictly speaking, I could put this in a coordinate system. This would be a coordinate x-axis, and then right along the left side of the gamma is a coordinate y-axis. So if I were to choose that coordinate system, as I seem to have done here, actually I don't like any of that drawing that came out there. So if I did choose that, then I could actually form vectors and do the cross product and all that good stuff. So I will give you a chance to see that in action. There's our x-axis, there's our y-axis. We have all that now. So in the case of the 25 Newton force, the lever arm vector is in fact 2.70 meters in the j hat direction. That should be obvious because, as I showed you, the lever arm for the 25 Newton force points from here to here, and that length is clearly 27 or 2.70 meters, and it clearly points in the positive y direction. Now, in that case, the force is a little more complicated because it's a 45-degree angle force, but we can see it has a negative y component right here, and it has a positive x component right here. So we know that it's just a matter of using the trig function. So F in this case would be 25.0 newtons times cosine 45, and that would be in the positive I hat direction, and then minus 25.0 newtons sine 45 degrees, and that's in the j hat direction. So that is completely true. I'm not necessarily wanting to use that way, but I might just to show you a third way of doing the cross product. So I probably will bring that up in a second. We can make that a little simpler by calculating what 25 times the cosine of 45 is. Of course, cosine of 45 is the same as the sine of 45, and that's root 2 over 2. But either way, 25 times cosine 45 gives me 17.68 newtons in the I hat direction, minus, and again, the sine of 45 is the same as the cosine of 45, so that gives you minus 17.68 newtons in the j hat direction, but notice that one was negative. So we have simplified it a little bit. But another thing we can do is we can use torque is equal to the component of F that's perpendicular to the lever arm times the lever arm. So we know the lever arm already has a magnitude of 2.70 meters, and we also know that the component perpendicular to it, remember the lever arm is this vector right here. So this component of the force is actually perpendicular to the lever arm because the lever arm is this guy. So for that reason, we just need the x component, and I'm going to go with the sign convention. I'll write it right here. Actually, I'll write it right here with red instead of laser pointer. So that's a typical symbol we use in engineering and physics for our coordinate systems. And it just means all the counterclockwise torques are positive, as well as the right is positive, as well as upward is positive. So, with that in mind, we can see right now, hopefully, y'all all can figure it out. Well, actually, let me ask you guys, and feel free to chat this or feel free to just blurt it out. What I'd like to know is what I'd like to know is that 25 Newton force, is that a clockwise torque or a counterclockwise torque? Anybody? Yes, that is a clockwise one. Very good. So that means it's going to be negative. So I'm going to put the negative in front of it. And now I'm going to take the 17.68 newtons. And by the way, that 17.68 newtons is not because I'm taking the y component. It is not because I'm taking the y component. It's negative because the torque is a clockwise torque. The 17.68 that I'm taking is actually the x component because that's the one that's perpendicular to the lever arm. And then I'm going to multiply that by the lever arm, and that's 2.70 meters. So I automatically get 17.68 times 2.70, and that gives me 47.73 negative. Newton meters, and that is something you might recognize as a common unit that we've used before. And it is, but we don't use that. Okay, so the Newton times the meter when we're talking about torque will stay as a Newton meter, whereas when we were talking about energy and work, the Newton times the meter became a joule. And in that sense, they are completely unrelated. So you should never be adding torques to work, and you should never be adding torques to energy or anything like that, even though the units look the same. So now we've gotten one of the torques calculated. I'm going to show you another way to calculate that torque, actually, I'm going to wait and do all these first, and then I'll come back and recalculate that 25 Newton force with another way of doing a cross product. So now I'm going to move to the 30 Newton force. So 30.0 Newton force. Now, in this case, the lever arm is, let me remind you again, I've drawn it a couple times, but just to make sure we're all on the same page, that's the lever arm. And you see the lever arm actually has a component that is perpendicular to the force and another component that happens to be anti-parallel to the force. So this is the component of the lever arm that is perpendicular to the force. And this one right here is the component of the lever arm that's like parallel slash anti-parallel. So if we can figure out exactly what this component of the lever arm is, then we can use this one, which is the perpendicular component of the lever arm, R perp times the force. So that's what I'm going to use. Uh, Now, looking at this figure, what we see is from here to here, this distance is 2.70 meters. And then from here to here, this distance is 1.40 meters. And from here to here, this distance is 2.31 meters. So if I take, and actually, it seems a little less than obvious. Actually, I might not have done enough to allow that. But that's okay. I can still, maybe. Nope, it looks like I cannot. I was going on the assumption that when I drew this, that this point right here and this point right here would be the same height, but they're clearly not. So it's a little more complicated to get the actual uh, lever arm component that's perpendicular to the 30 Newton force. So I might have to add another measurement to this drawing, but let's check and see. So if I go up here 2.31, no, that doesn't help. Ah, well, I did use something very specific. I basically reached the conclusion that two of these squares is 0.70 meters. And what I see here is the distance to the bottom of that to the top of that is about half a square. So since that's half a square, that should be 1/4 of 0.70. One half of 0.70 is 0.35. One half of that is 0.175. 1725. Yes, 17. No, it's 175. 35 divided, well, 30 divided by 2 is 15, and then 5 divided by 2 is 2.5, so it's 17.5. So with that in mind, we can actually add this extra measurement, and I'll do that now as if we had it all the time. But what I'm going to do is say the distance from here. Actually, the best way probably wouldn't be do it that way. The best way would be draw it like this. And then let's call this distance 0.175 meters. Okay. Now that we have that, we can figure out exactly how high this spot is right here. So where the point of application of the 30 Newton force is, and by the way, that 30 Newton force is supposed to be horizontal. This 57 Newton force is supposed to be vertical. That's supposed to be fairly trivial. So if I want to figure out the component of the lever arm perpendicular to the 30 Newton force, what I can do is R perp 30 Newton is equal to, what I'm going to do is try to add my way up to get that total length. And I see that's 2.70. That gets me up to this dot right here. But I need actually to go up to this dot here. So that's a little more complicated. That one might not be helpful at all. In fact, no, I'm not. I'm not going to do it that way. I'm going to take the inside one. Whoa, that was bad. I am going to take the inside one, which is this measurement right here, and I'm going to add that. So we're going to say 2.31 meters. Now I want to go from that height to where the actual 30 Newton force is applied. In order to do that, I happen to know the distance from the bottom of this letter to the top of that letter, but I'm already past that. I'm up to here, so I need to subtract that small amount right there. So now I'm going to say minus 0.175 meters. That brings me to this height right here. And now I need to add 1.40 meters. And that gives me 2.31 minus 0.175 plus 1.40 equals 3.535. Now we can tell that that last five is an extra digit. It's not really a sig fig, but that is the component of R perpendicular to the force. Because remember, again, the lever arm is this vector, but that vector has this component, which we just calculated, and this component, which we don't need. Not yet, anyways. So now we can say torque, and I should call this one 25. Torque 30 is equal to, you can see probably that this 30 Newton one, does everybody agree that that's a counterclockwise torque? Anybody have any problems seeing that that is counterclockwise? Since it's counterclockwise, I'm going to go ahead and put a positive symbol on it. And I'm going to say R perpendicular 30 times F30. And the R perpendicular we found was 3.535 meters times the force, which is 30.0 newtons. So if I multiply this by 30, I get 106.05 Newton meters. Now that was only good to 3 sig figs, so the 0 and the 5 are not sig figs, but that is the torque due to the 30 Newton force. So we've now used R perpendicular times F. Now it might be a good time to find the component of F that is perpendicular to R, so I could use the other formula. None of these jump out at me as really easy to do that, so I might have to force it. So let me go ahead and say we're going to tackle the 57 Newton force. So 57.0 Newton force. In this case, I'm going to go ahead and draw the lever arm, and I'll draw it first in laser, but I want to draw it as well actually on the diagram. Let's use a color we have not used. I think I'm going to use purple because that'll stand out nicely. Now, I just drew that and used my quick drawing program that would allow me to make the picture look a lot better. So there's your lever arm vector, and that's the lever arm for the 57 Newton force. Okay. Now we can, in principle, figure out exactly what angle that is and then figure out the angle between them because once we put the vectors tail to tail, we could use that to compute the component of it that's perpendicular. Or I can look at it and notice that I can make a line like this that's perpendicular to that vector. And then it's just this component of force that we need. In order to do that, though, I would, of course, need that angle. Well, I know that this angle is the same as that angle because this force I already told you was vertical, and this one is meant to be vertical. So this angle and this angle are the same. Now, if we can figure out exactly how far to the right this purple vector points, then I can easily tell how high up it points, and we can then use the trig function to compute that. So, for instance, we could say, let's look over here. I'm going to say that we have this vector that leans like this, and we're wanting to hash this out and figure out exactly what this angle theta is here. So this is supposed to be this drawing that I put in the bottom left corner of the page. That's supposed to be a drawing representing that bigger purple one, but I don't want to draw it on that bigger purple one because it would cloud up the image so much that you wouldn't be able to make out anything. Now, what we do know is it comes down to the bottom of the 1.40 meter part, and we know that that is in fact 0.175 meters lower than the 2.31 part. So that tells us that this side right here, which I'll call R57Y, that R57Y can be written as, or can be calculated as, that's going to be 2.31 minus 0.175. And that's in meters, of course. I didn't write it there, but we're going to at the end. 2.31 minus 0.175. That gives me 2.135 meters. Now, just to check, I'm going to go ahead and make sure I did correct when I divided that zero point 0.7 by 4. And it was 0.175. So I just wanted to make sure I had my arithmetic right. I'm always making careless arithmetic mistakes, so I just want to make sure I didn't do that again here. So now I've got that. Now I've got to figure out how far horizontally it is. Well, what we know is the whole width is 1.72. That's from the left-hand side all the way to the far right-hand side. And if I want to know the width to the little dot right here, then all I need to do is take this whole width, which is 1.72, and then subtract this, which is zero point 0.7. So this is what I'm going to call R57X. So R57X is going to be 1.72 meters. That's the full width minus the width of the vertical part, which is minus 0.70 meters. And that gives me, of course, 1.02 meters is the component there. So this means that theta is equal to the tangent inverse of the x component, which is 1.02 meters, divided by the y component, which is 2.135 meters, like that. And I'll take tangent inverse, so I hit shift tangent inverse, and I take 1.02 divided by 2.135, and that's going to give me 25.54. So that angle right there is 25.54 degrees, and that means this angle is also 25.54 degrees. So if I want the component of F perpendicular to the lever arm, then I just need to take F and multiply it by the sine of 25.54. So that means F perp is equal to the force, which is 57.0 newtons, times the sine of 25.54 degrees. And if I compute that, I get 20, 57 times sine 25.54 gives me 24.57. It's actually 24.58 newtons. So now I have F perp and therefore torque 57. And by the way, the 57 Newton force is also a counterclockwise torque, so it's positive. So now all I'm going to do is take F perpendicular and multiply it by R. Now, you can see the problem with this is we don't know the length of r because that's a vector we just made up, but we could go ahead and use the Pythagorean theorem and compute that if we wanted, and that would be fine. But there actually might be a much better way. I've worked this all out so that you can do it any way you possibly want, but you might notice that the 57 newtons is in fact exactly perpendicular to the x component of the R57. So when we're talking about the lever arm being for the 57 Newton force, remember one of the torque formulas is the force times the component of the lever arm that's perpendicular to the force. So that is a much better, easier way of doing it. I'm going to do that now, and I'll write it in blue just so it'll stand out. So I'm going to say torque 57 is going to equal the x component we found was 1.02 meters. And remember, that's horizontal. And then the actual force, which is vertical, is 57.0 newtons. So 57.0 times 1.02 gives me 58.14 Newton meters. And that's one extra digit than's acceptable. Okay. So now we have all of our torques. One torque is negative, and that's 47.73. So the net torque equals negative 47.73 Newton meters. And remember that 3 there is a non-significant figure. Now we have the 30 Newton force and the 57 Newton force. For the 30 Newton force, we got 106.05, and that was positive. And then for the 57, we got 58.14 Newton meters for the torque. So the sum of all these will be 106.05 plus 58.14 minus 47.73. That gives me 116.46 Newton meters, and that should be the net torque. If you'll notice, though, the 106.05 means that the tenths place is not significant. And of course, all of them tell you that the hundredths place is not significant. But once the tenth was, then clearly the hundredths can't be. So we'd have to round this to one sig, I mean, to three sig figs total. So the torque net, which is also equal to the summation of the torques, that is the answer that we were seeking. I've actually calculated all the other torques because that was what the problem asked for. It says calculate each torque and the total torque. So I'm going to go ahead and write this as equal to torque 25. Circle that off. Actually, I don't like that circle very much at all. I'll box it off this way. I found the torque for the 30 Newton one. That's going to be this quantity. And then finally, I found that the torque for the 57 one was positive 58.14, like that. So we got that. Now, the other thing I mentioned to you is that we can actually, since I took the time to compute what the force vector is and what the lever arm vector is for the 25 Newton force, I can go ahead and calculate this with a cross product, and we can use that to verify that we got the same formula. So I'm going to do that, and I'm going to do it by stealing these results right here. So I'm going to lasso them, and I just asked it to copy that. Now I'm taking it, whoa, just moved it by mistake. Now I'm going to paste it right here on this page. So now I can say torque is equal to R cross F, and I'm going to write this in blue. So in this case, I'm going to say torque for the 25 Newton force is equal to. Now, in this case, you could actually put it all in the determinant, and I highly recommend you take the time to do that, put that in a matrix, and then take the determinant of the matrix, just the two ways that I showed you last time, to make sure you get the right answer. But now I'm showing you yet a third way that actually makes it a lot easier. And in order to do it, what you need to do is just draw a right-handed coordinate system. I'm going to draw that right here. This is going to be my x-axis coming out of the board or out of the screen. This is going to be my y-axis, which is on the screen but pointing to the right. And if you'll notice, that does match the right-handed scenario where your index finger is the positive x direction, your middle finger, which is 90 degrees from the index finger, is the positive y direction, and then your right thumb points in the direction of the positive z component or z direction. So that is our right-handed coordinate system, and all our coordinate systems need to be right-handed for reasons that I've mentioned before. So with that in mind, now let me show you how we're going to go about doing this. This one's actually a little easier because we only have two components, so it takes a little less time. But what we're going to do is we're going to say this is 17.68 newtons I hat minus 17.68 newtons J hat cross. So notice I just put that big old cross right in there. Crossed with 2.70 meters J hat. Okay. Now the trick to this third method is I'm just doing the distributive property, but the distributive property across a cross product. So I'm going to take this component and cross it with that. And you got to remember, a cross product isn't like a lot of things. A cross product, A cross B, is innately different than B cross A. So you can't flip the order. So everything that's on the left has to stay on the left hand side of the big X symbol, and everything on the right has to stay on the right of the big X symbol. So what I'm going to do is take 17.68. I'm going to drop the units, by the way, here too, just because it's becoming cumbersome to write all that stuff and confusing. So I'm going to take the 17.68. I'm going to multiply that by the 2.70. What I'm using here is a property called linearity, and the cross product, like the dot product, is a linear operation, and that means that you can sort of pull out if you have a dot product or a cross product where the two things that are being multiplied have multiple terms with scalars in them, then you can pull all the scalars out in front and just allow the dot or cross product to apply only to the vector parts, and you don't lose any information and you don't make any errors. So in this case, what I did is I pulled the 17.68, which is a scalar, out to the left, the 2.70, which is a scalar, out to the left, and now all I have left is I hat cross j hat. Notice how I did keep the I hat on the left and I did keep the j hat on the right. That's absolutely essential. Now that I've done that, what I need to realize is I hat cross j hat is, according to the right hand rule, remember the right hand rule is this is your first vector, and I hat's pointing out of the board, so I'm pointing it towards me like that. Your second vector is j hat, and that's this one. And this one doesn't necessarily have to be 90 degrees. It is when we're using it to make a right-handed coordinate system. But if we're using it to do a cross product, it's any angle that you want it to be. But if the angle turns out to be 0 or 180, then the cross product's going to be 0. But if it's any angle other than those two, then it'll be non-zero. So the main thing is I'm going to take the I hat cross j hat, and that points in the upward direction, which is the positive k hat. So what that means is the 25 Newton uh, or 25 Newton force causes a torque that points in the positive k hat direction, cause I hat cross k hat, or excuse me, I hat cross j hat is equal to k hat. Now, we're also making use of the fact that A cross B is the magnitude of A times the magnitude of B times the sine of the angle between them. Well, the magnitude of I hat is 1. The magnitude of J hat is 1. And the angle between I hat and J hat is 90 degrees. So it's 1 times the sine of 90. Which gives us 1 as the magnitude and K hat as the direction. Now I'm trying to make sure that this, in fact, gives us what I would normally call a positive direction. Counterclockwise is supposed to be positive. Yes, yes, that is consistent with it. That's the other thing. You got to be careful when you make up a torque positive sign. If it's not consistent with the X and Y hat and you go and compute this, then you'd actually get off by a negative. So this one comes out positive, which is exactly what we expect. But if I had done, instead of this as my sign convention, if I had done clockwise was positive, then that would be inconsistent with the definition of X and Y. And therefore, what I was calling negative torques would be positive torques, and what I'd be calling positive torques would be negative torques. As you can see, positive torque in this reference with that particular coordinate system chosen means the torque points in the positive k hat direction, and negative means it points in the negative k hat direction. Now I've just done one of those. Now I need to do the other term of the first vector. So I have to distribute this one to hit here as well, and I'm going to do it the exact same way I did before. So we automatically just say they're connected by addition. If a multiplication by a negative gives us a negative, then that's going to change it, but that's okay. Now I'm going to pull out the scalar from the left vector, which is negative 17.68. And I'm going to pull out the scalar from the right vector, which is 2.70. Notice I am dropping the units still. And now I have to have the actual vectors operate, and the left one is a j hat, and the right one is a j hat. So j hat dot j hat is 1 times 1, because both j hat and j hat have magnitudes of 1, times the sine of 0 degrees, because j hat and j hat are parallel, so the angle between them is 0. So that means this is our 0 vector, and in fact our total torque is just this answer, 17.68 times 2.70 positive times 1. It gives me positive 47.74 Newton meters in the k hat direction. Okay, so that is the torque for the 25 Newton force. We did find, in fact, that it was 47.74, 47.73. In this case, we called it negative. Let's see. Is that the same one? 47.73, 47.73. That was the 25 Newton force. Oh, the 25 Newton force was what we called a clockwise torque. And a clockwise torque should have given us a negative. Let's see if I did anything wrong with that. I found the force was the y component was negative 17.68. The x component was positive 17.68. So that all looks fine. And then the r vector was just 2.70 meters positive. So r cross f, that should have gave us a negative. Why did I not get a negative? R cross F. R was 17.68. Hmm. I hat cross J hat gave us K hat. That's right. I don't know why I didn't get a negative there, but that's 47.73 newtons. I did get the right figure. That's the sign. The magnitude is the important part. But I'm just curious. X, Y, Z. Yeah, a counterclockwise torque should be positive, but in this case we have a clockwise torque R cross F definitely points in the negative direction. I don't know why it didn't come out as a negative, but we'll leave it at that just because I don't want to waste a lot more time on that. But that's something to think about. If anybody wants to figure out what, if anything, went wrong, that would be great. You can write that up, send it to me in a text message, and I'll give you extra credit for it. I'm going to be thinking about it to try to figure out what happened, but it definitely seems in the case of the R57 cross 57 and the case of the R30 cross 30, they definitely give me positives, but for some reason the 25 should definitely give me a negative. R cross F should give me a negative, but for some reason it came out positive and I don't know why. So, anyways, anybody have any questions on all this junk that we just did? That's a pretty exhaustive example of torque, and in most cases you can do a lot less, but this one's kind of nice in that you see a bunch of different ways I can do it. I showed you more or less how to do it with R times F perp. I did do R perp times F. I did do RF sine theta to some extent, and I also did a cross product a new way. You can also do the cross product the original way. And actually, let me do the cross product the original way just to show you. that, and that won't be any harm. So torque is equal to R cross F is the determinant of, now my first row is I hat, J hat, K hat, and then my second row is the R vector, so that's 17.68, and then minus 17.68 because the Y component is minus, and then 0, and then my force is just in the Y direction. This was the 25 Newton force. Oh no, my force was, there you go. I just figured out why I did it backwards. I did F cross R instead of R cross F. That's why. So yeah, that's the R is right there. Yep, I did F cross R. It's obvious that I did it now. So to fix this, I'm going to say equals negative F cross R. Therefore, I'll just stick a negative in front of there and a negative in front of there, and that ultimately gives a negative. So now we see that we got the exact right answer. Uh, that should have been something I noticed. You guys, it would have helped if you noticed it, but it's certainly not reasonable for you to do it because this is literally the first physical example that you saw of torque. But notice I did actually put the vectors in the wrong order. And of course, that was sort of one of the points I was trying to teach you was that you can't, reverse the order of the cross product because that gives you the wrong answer. It in fact reverses the sign. A cross B is the negative of B cross A. So in this case, now we see that the torque did come out to be what we expected, and you can see how you're going to report it here. I need to put R as the first vector, not F, and that's what I've done here is put F as the first vector. So the R as the first vector would be putting a 0 here, a 2.70 here, and a 0 there, and then a 17.68 there, and a negative 17.68 there, and a 0 there. And then we could copy it again if you would like that last method I showed you. That would be a 0, 17.68, and then a J would be a 2.70 and a negative 17.68. I just had to get enough room, so I wrote it that way. So if I do the top left to the bottom right, this one gives me 0 because I times 2.7 times 0 is 0. This one also gives me 0 because there's a 0 in that one. And then this one also gives me a 0 because the 0 under the I hat. Now I'm going to do minus, which I'll do with green. So this will be minus 17.68 newtons. The minus I put in there because I'm going from the top right to the bottom left, which is the subtraction direction, times 2.70 meters times K hat. Now, if we look at this one, we get 0. And if we look at this one, we get 0. So in fact, we got 0 for this guy, we got 0 for this guy, we got 0 for this guy. And in fact, our only answer was the final answer, which is negative 47.74 Newton meters. And I don't know why I'm drawing these fat ends. Newton meters K hat. So now we've seen yet a 15,000th way of calculating the torque. Any questions on that? I'm glad we caught. I'm glad I caught the error or figured out what it was. Sorry I made it. Anybody have any questions? And I did see your comment, Darius. We'll talk about it at the end of class or during break or something. And don't worry, I got you covered, man. Anybody have any questions on this? Okay, so your book does plenty of examples on calculating torque. I highly recommend you look at all those examples. But what we can also do now is go ahead and try to compute some of the other stuff, some of the other examples. I'd say the only one that's really even remotely complicated enough for you to take any practice in is example 10.8 in terms of the torque, but even that one's pretty straightforward. If you look at example 10.8 on page 274, you'll see that we have a circular disc on the front of which is mounted another circular disc that's slightly smaller in radius. And on that slightly smaller circular disc, we have a force pulling straight downward of 50 newtons with that little radius. And then on the bigger disc up at the top, we have a force pulling up and to the right at 30 degrees above horizontal. And that, of course, creates a torque. You can probably realize that the force pointing down and attached to the small radius is a counterclockwise torque, and the torque on the large disk is a clockwise torque, and it's just a matter of calculating them. So let me just do that rather quickly. I was going to sort of explain it and talk about it, but I think it might just be best to go ahead and compute it. So let's move on to example 10.8. So what we have here is a circle. Hmm, I hate it when I draw a circle because then it won't let me just move it easily. Okay, let's see if I can get it sort of centered. Okay, that looks good enough. So what we're going to say is this radius is RA, and this radius is RB, and I'm going to say RA is equal to 30 centimeters, and I'm going to say RB is equal to 50 centimeters. I'm assuming there are two sig figs on that. I'm going to also say that right up here, I have a force acting at a 30-degree angle. And this is FB equals 50 newtons. Again, assuming two sig figs there. And this is 30 degrees. And we also have this force right here, which is FA equals 50 newtons. And we're asked, it says two thin disc-shaped wheels of radii RA equals 30 centimeters and RB equals 50 centimeters are attached to each other on an axle that passes through the center of each, as shown in figure 1017. Calculate the net torque on this compound wheel due to the two forces shown, each of magnitude 50 newtons. Okay, so if you look at this, you can see this would be our lever arm. So that's R sub B lever arm, meaning the lever arm for force FB. And of course, you can figure out that the component of F perpendicular to that would be the cosine of 30 degrees times the 50 newtons because we want the component that's in the x direction. We also notice that the FB is a counterclockwise torque. So again, we use our sign convention. We're saying counterclockwise would be a positive torque, and this FB 50 is a clockwise torque, so that's going to be a negative. So now I can go ahead and say the torque B is equal to RB, because that's the radius, which is, of course, 50 centimeters, times the component of R perpendicular. So what I'm using here is the component of F perpendicular to R. So what I'm using here is R times F perp. Now F perp is going to be 50.0 newtons times the cosine of 30 degrees. Now, you'll notice those two vectors are not strictly speaking tail to tail. That's why I'm using 30 degrees. If I actually considered them being tail to tail, I would slide that purple vector up until the tail of it was at the tail of the red vector, and then you'd see the angle between them is 60. So I could have written F perpendicular as 50 newtons times the sine of 60, and then it would look more like RF sine 30 or sine theta. And that's perfectly acceptable as well. So I'll say, or 50.0 centimeters. Notice I'm using centimeters here. That's not necessarily a good thing to do, but I can fix it in a second. Times the sine of 60 degrees. Because when you put the RB so that it's tail to tail, you'd see that this angle is 60 degrees. So in this case, I'm using R times F times the sine of theta. But in this case, I'm using F perp is 50 times the cosine of 30. Now, either way, I get the right answer. And it's going to be 50 times 50 times cosine 30. Now remember, we're off because this is in Newton centimeters. So this is 2,165 Newton centimeters. And since this is a clockwise torque, we're going to call that negative. So I just forced that sign there. If I did the other one, notice 50 times 50 times sine 60, you get exactly the same thing. Negative 2165 Newton centimeters. So what we're going to do is we're going to say torque B is negative 21.65 Newton meters. Notice I went ahead and dealt with the centimeters by dividing by 100 to convert the centimeters to meters, and that made it go from 2,165 to 21.65 with only the two sig figs that we had. And now I'm going to calculate the torque due to A, and in this case, you can see that the lever arm RA is automatically perpendicular to the force, so we don't even have to do anything complicated. We just multiply the two numbers. So I'm going to say torque A, and this one's a clockwise, a counterclockwise one, so I'm going to say is positive 50 newtons times 0.50. Excuse me, that was centimeters, but since I wrote it as 0.50, it's meters. So 50 times 0.50 is obviously 25. So this gives me positive 25.0 Newton meters. And therefore, the net torque, I'll leave the vector symbol off, equals torque net is 25 minus 21.65. And that gives me 3.35 Newton meters. Now notice we technically didn't have any decimal places that were significant here, so technically this now only has one sig fig. So that's our final answer. Anybody have any questions on that one? The positive suggests it's counterclockwise, by the way. No questions? All right, so that's plenty of stuff. Oh, what's happening here? Oh, stupid me. Anybody notice the mistake I made on TA? Anybody catch that? Remember, TA is supposed to be force A times lever arm A, but lever arm A was not point 0.5. That was me just being careless. So I'm going to write in the correct figure, which is 0.30. And then, of course, that means this answer is not quite right. So I'm going to say positive 50 times zero point 0.3 equals 15.0 Newton meters. Now we've got a whole different dynamic going on. We have the net torque is equal to 15.0 Newton meters minus 21.65 Newton meters. And I can't say it's counterclockwise because it's positive, because lo and behold, it's now going to be negative. So I got to erase that, which I had saved because I was hoping it would still come out the same, but it did not. So 15 minus 21.65 gives me 6.65 negative Newton meters. And again, the sig fig rules dictate that neither one had any decimal places, so the answer can't have any decimal places. Hence, this is only a one sig fig net torque. And the fact that it's negative means that it's clockwise. Okay. So that is how we do that one. Your book ended up getting negative 6.7, so that's good too. Anybody have any questions on that? I'm worried about the dearth of questions I'm getting, so please, folks, ask questions. Not only that, I'm worried that you aren't catching, like that careless mistake there where I put in point 0.5 instead of 0.30. I would hope that y'all would catch that. That makes me worried that you're maybe not paying attention while you're in here, and you're just, here to try to show me respect and be, kind and showing up for class. But if you're not paying attention, it's not going to help you very much, folks. At least we got a video recording, so you can always check that out later. All right, now that we have that, we can start using our rotational dynamics, which requires us to be able to calculate moments of inertia because that plays the role of mass in rotational motion. Remember, F equals ma is actually the net force is equal to ma, but it's actually the net force is equal to dp dt. Well, the rotational analog is the net torque is equal to I alpha, where I is the moment of inertia. But the more general one is the net torque is equal to dl dt, where L is the rotational moment of inertia, or excuse me, the rotational, the rotational momentum, the angular momentum. That was the word I was going for. So, anyways, that's something we can work with. What I want to do now is figure out how we can use this new law, and let me restate it again, just in case anybody forgot. The new Newton's second law is the summation of the torques is equal to I times alpha. And that's the ideal scenario if the moment of inertia is not changing, anything like that. Of course, we could also generalize it to say the summation of the torques is equal to dl dt, and L is equal to R cross P. But L is also equal to I omega, where omega is that pseudo vector we talked about earlier. So those are all things we can use. Now, what they're going to tell you is, and I want you to understand that this equation is only valid. This equation right here is only valid for an axis fixed in an inertial reference frame. So the axis has to be fixed in an inertial reference frame. Uh, your book says in the paragraph below it, it says this is the rotational equivalent of Newton's second law. It is valid for the rotation of a rigid object about a fixed axis. Equation 1014 is valid even when the object is translating with acceleration, but only if we calculate I and alpha about the center of mass of the object and the rotation axis through the center of mass doesn't change direction. So that's a really big, important paragraph that you have to understand to be able to apply these this actual equation. So another way of writing it is the summation. Oops, let me go back to my purple. Another way of writing it is the summation of the torques about the center of mass is equal to the moment of inertia about the center of mass times the angular acceleration about the center of mass. So this is for axis fixed in direction but may accelerate. So calculated about the center mass, the axis is fixed in direction means a rolling wheel makes no left or right turns. Okay, so a wheel rolling down the street would be a fixed axis, but if you see when you do let a single wheel roll down the street, it often doesn't just go in a straight line. Sometimes it curves a little this way and that way. That wouldn't be applicable. In other words, we can't use this equation if we're allowing the axis of rotation to rotate. Now that we have all that, let's do some examples. So example 10.9. So again, I'm using the book's example. This is example 10.9. It says two small weights of mass 5.0 kilograms and 7.0 kilograms are mounted 4 meters apart on a light rod whose mass can be ignored, as shown in figure 1020. Calculate the moment of inertia of the system A when rotated about an axis halfway between the weights, and B when rotated about an axis 0.50 meters to the left of the 5 kilogram mass. So this will be a lot easier when I draw the actual figure. So what I'm going to do is I'll draw like a y-axis, which I just generally draw axes. You don't necessarily have to in every case, but I do just because that's what I like to do. Okay, what I'm going to say is right here we have the mass of 5.0 kilograms, and right here we have the mass of 7.0 kilograms. And we know that the distance between them is 4.0 meters. In part A, the axis is dead center between the two, so that this is 2.0 meters. In part B, they want the axis to be 0.50 meters to the other side. So what I'll do is I'll write this as a green one, and I'll say, and that's for part B. Okay? So what they've asked us to calculate is we have all the figures right here, and what they want us to calculate is the moment of inertia. Okay, let's start off with part I, or excuse me, part A. Let's start with I. Okay, so the solution is What we found is the moment of inertia I is equal to the summation from I equals 1 to n of m sub I r sub I squared. So what we need to do is find r sub I for each of them. In this case, we only have n equals 2, so there's only going to be two terms. But r sub I is the perpendicular distance from the center of mass of m sub I to the rotation axis. Okay, so it's got to be perpendicular to the rotation axis and then measured from and perpendicular to that rotation axis to the center of mass of the other one. If you're dealing with point objects, then it's not that big of a deal because the center of mass is their location. So in this case, we're going to go ahead and start with part A, and we're going to say I is equal to 5.0 kilograms times 2.0 meters squared plus 7.0 kilograms times 2.0 meters squared. And in this case, we get 20.0 kilograms meters squared plus 28.0 kilograms meters squared. Our I for part A is equal to 48.0 kilograms meters squared, and that is the units that we expect for moment of inertia, kilogram meter squared. Anybody have any questions on that one? Now for part B, it's a little more complicated, but it's really a pretty straightforward process. So now our rotation axis is to the left of the 5 kilogram object, and therefore m sub I r sub I squared from I equals 1 to n becomes 5.0 kilograms times 0.50 meters squared plus, now notice the green axis is a whole 4.50 meters from the 7 kilogram one. So this is 7.0 kilograms times 4.50 meters, and that's going to be squared. And I didn't draw that very well, so now what I have is 5 times zero point 0.5 times zero point 0.5 gives me 1.25 kilograms times meters squared, and then 7 times 4.5 times 4.5 gives me 141.75 kilograms meters squared. Now that was only 2 sig figs multiplied by 2 sig figs, so technically even the ones place, much less the tenths or the hundredths place, is not significant. So we actually have to round this to basically the nearest tens. So I for part B must be 143.00 kilograms meters squared, but the 3 is not significant, nor is the 0 or the second 0. So we'd have to call this roughly 140 kilograms meters squared if I stuck with the proper sig fig rules. Your book is not sticking with the proper sig fig rules and just called it 143. Anybody have any questions on that? All right. So now we need to also do some examples of calculating the moment of inertia. Your book has a really nice table. It has the moment of inertia for a thin hoop. That's a thin hoop measured, or the moment of inertia for a thin hoop measured when it's rotated about an axis perpendicular to the hoop. Then they handle it for an axis parallel to the hoop. Then they do a solid cylinder with the axis perpendicular. Then they do a hollow cylinder with the axis perpendicular. Then they do a sphere, a uniform rod about its end, a rectangular plate, all that good stuff. All of those are good formulas to use. Notice they're always some number times a mass times some quantity squared, or in the case of like the hollow cylinder or the rectangle, you have some number times the mass times parentheses a sum of squares. That's all in table figure 1021, which is a table. I'm going to show you how to actually do a calculation to calculate the moment of inertia of something using the calculus. So let me show you an example for this. So this is just example. What I'm going to do is draw a coordinate system because it makes it a little easier to specify what I want. There's my x-axis, there's my y-axis. What I'm going to do is draw a uniform rod, which you might think of like a broomstick or something like that. And let's say its length is L and its total mass is M. So a broomstick has a length L and a total mass M that is distributed uniformly. What is I if rotated about, whoa, the left end? What what if rotated about x equals L over 2? So what we're saying here is in part A, we're using a rotation axis that is the y-axis. And in part B, this is the rotation axis. Okay. Now, what I'm going to do is I'm going to recall that solution I is equal to the integral of r squared dm. And like I've told you, dm should be considered a linear mass density lambda times dl, or a two-dimensional area density sigma times differential area element, or a three-dimensional density rho times a differential volume element. Okay. Now, when we use that, if we're told that the mass is uniformly distributed, then that means lambda or sigma or rho will be a constant. And that's what we have here. So let's start off with part A. I'm going to draw a little mass segment, and I shall draw it in green. So this is my differential mass element. And of course, it's a one-dimensional broomstick because basically the radius of the broomstick is way smaller than the length of the broomstick. So the vertical dimension, which is the diameter, and the in and out dimension, which is also the diameter, they're both very, very small compared to the length. So we're treating it like it's a one-dimensional object because the vertical measurement and the in and out measurement are insignificantly small. With that in mind, I'm going to say dm is equal to lambda times dl, but notice dl is actually parallel to the x-axis, so we should call it dx. And not only that, because this thing is oriented such that the left edge is at the origin and the right edge is along the x-axis, as is the whole body, then the dimension measured perpendicularly from the rotation axis to the dm is actually x. So this distance right here is x, and that is our r. So now I can say I for part A is equal to the integral of r squared dm. Now I'm going to substitute the fact that r is just x squared and dm is lambda dx. Now, given dm is equal to lambda dl and lambda is a constant, then lambda is equal to dm over dl, which in this case is just mass per length because it's a constant. So even if I took the little differential mass dm and divide it by the little differential mass dl, I'd get the same thing as taking the whole mass m and dividing it by the whole length l. So that's why I could just write it as m over l. That being said, I'm going to integrate from x equals 0 to l, and the lambda can come out in front, and I'll get lambda times the integral of x squared dx from 0 to L. And the integral of x squared is 1/3 x cubed. So I'm going to have 1/3 lambda, and then x cubed evaluated at L is L cubed, and x cubed evaluated at 0 is 0. So this is going to be 1/3 lambda L cubed. But lambda now is m over L, so I'm going to say 1/3 m over L times L cubed. You can see that the exponent of 3 is going to cancel out, leaving an exponent of 2. And we now have that the moment of inertia is equal to 1/3 ml squared. And that is the moment of inertia for a rod rotated about its end. Okay, and that exactly matches the table that I told you about. Now, if I want to try part B, I'm going to rotate it about its center, and we can still use, for instance, we can move the origin of our coordinate system to L over 2, and then it'd be basically a setup where we're going to integrate from negative L over 2 to positive L over 2, but the dimension, the distance from the origin to the DM is again going to be X. And the fact that x goes from negative L over 2 to positive L over 2 will take into account the fact that some of the mass is to the left of the origin and some of the mass is to the right. So I'm going to say I for part B is equal to the integral of r squared dm, and that's going to be the integral using the exact same differential mass elements and all that good stuff is going to be x squared times lambda dx. Only I'm going to integrate it from x equals negative L over 2 to L over 2. So that's the big difference. I've sort of imagined, even though I didn't take the time to draw it, I've imagined moving the y-axis to what was originally called x equals L over 2, but now is going to be called x equals 0. And then what was x equals 0 is going to become x equals negative L over 2. And what was x equals L is going to become x equals L over 2. So the 0 is going to become x equals negative L over 2. And the right end is going to become x equals positive L over 2. Again, I pull out the lambda out in front and I get 1/3 uh, x cubed, but x cubed evaluated at L over 2 is, I'll actually write it out because this is a little bit more complicated arithmetic. So I'm going to say positive L over 2 cubed minus negative L over 2 cubed, like that. I'm also going to make use of the fact that lambda is m over L, so I'm going to say m over L times 1/3 times 1/3 times, now this is going to become L cubed over 8, and then negative L over 2 cubed is going to be negative times a negative is positive times a negative is a negative, and then a negative being subtracted becomes a positive, so this is going to be plus L cubed over 8. So that is 1/3 m over L times L cubed times 1 over 8 plus 1 over 8, which is obviously 2 over 8, which is 1/4. So we get 1/12. Ooh, I wrote that badly. So we get 1/12. I wrote it badly again. ML squared is I for part B. So that's how you go about calculating the center of mass. At least that's one particular case. Now let me show you one more. Calculate the moment of inertia of a uniform cylinder. That word cylinder did not come out well. Of mass m, radius r, and height h. If it is rotated about a perpendicular axis through its center of mass. Okay, so what we have here is, I want to make a copy of this. So this is our actual cylinder, and it's sort of drawn in transparent mode so that we can see the backside, but I can fix that really quickly by making sure that the part we shouldn't be able to see is dashed. So we see that. We know the height is h. We know the radius. We know the radius is r. And we know the mass is m. And we also know that rho equals a constant. Notice it's a three-dimensional object, so rho is the typical density that we're going to use, but that's what we're going for. Now, what's smart for me to do here is go ahead and make a coordinate system. So there's my x-axis. Let's say there's my y-axis, and there's my z-axis. Okay. Now, what I need to do is use solution I is equal to the integral of r squared dm. Now, the trick with this, just like it was with the center of mass, there's a integrand, in this case r squared, and then the differential dm, okay? We have to choose a dm that has the integrand very well defined. In other words, if the integrand, if the r value varies wildly, macroscopically even, uh, across a DM differential mass element, then we'd have to do some other process of figuring out what the average R is for that process. But if we choose a DM that has an R that only varies by a differential amount, then we can use that R and integrate accordingly. So what what I'm going to do is choose basically a little uh, cylindrical, let's say, soup can wall without the lid, without the bottom either, but just the soup can wall, so that the wall of the soup can is, in fact, infinitesimally small. It's going to go, in fact, the radius to the inner edge of the soup can wall will be r, and the radius to the outer edge of the soup can will be r plus dr. But the soup can wall will be h tall, and its radius will be r, where r is some value between 0 and big R, the radius of the object. So my differential mass element, in fact, is going to be something like this. Actually, I'm going to try to draw it with the tool on that makes it a nice figure. That's pretty good. Like that. That is the top of our little differential mass element. Now this one I drew just a little bit crooked. Okay. Now I'm going to take this guy and do copy, paste, and now I'm going to take this outer guy and try to copy it too, so we can get a really good drawing, but let's see if I can grow it up bigger. It's not letting me do it. Okay, well, I'm just going to wing it and see if I can draw it neat enough. Okay, so that's our differential volume element. And therefore it's also our differential mass element. It's that whole thing that we drew right there. And you might not like what we use. If you've ever used this in your Calc 2, you probably were a little bothered by the formula you use. For instance, what I'm going to do is I'm going to say dm, which is what this red thing is equal to rho dv. And I'm going to say the radius is r. What I'm going to say here, though, is rho. And then dv, I'm going to say is 2 pi r. That's the distance around the inside edge, because that's out of distance r, and therefore 2 pi r is the circumference. Now, if I multiply that by the thickness dr, that sort of gives me the area of the top surface. You know, it's a little bit off, but that's pretty close. And then if I multiply it by h, then that'll be the whole volume. So the differential volume element is 2 pi r h times dr. Now, in principle, what it really should be is pi. Let me write it this way. It should be pi r plus dr quantity squared minus r squared times h. That should really be the volume of this, because obviously a pi r plus dr is a cylinder whose radius is r plus dr, uh, and whose height is h. That's what pi parenthesis r plus dr close parenthesis squared times h is. And then pi r squared times h is the cylinder that's being subtracted out of the middle. That is the actual exact formula. But if you compute this, you're going to see that you get pi times h times r squared plus 2rdr, excuse me, 2rdr plus dr squared minus r squared. And you can see immediately that the r squareds are going to cancel out. And the dr squared, since we're taking in calculating this integral, we're doing a Riemann sum, and that's going to basically take the limit as the dr goes to 0. So if the dr goes to 0, dr is really, really small, but dr squared is super, super small. So we can say dr squared is approximately equal to 0. And now you see you get 2 times r times dr times pi times h, which is exactly the formula we're using. So that's why that works. Let's go ahead and compute it now. We're going to say, and by the way, rho, since dm is equal to rho dv, that means rho is equal to dm over dv, which equals m over v. And of course, v is pi r squared h. So that's what rho is, just like we did with lambda before. Now I can calculate I is equal to the integral r squared dm. That's going to be the integral of r squared times rho times 2 pi r h dr. So I can pull the 2, the pi, the rho, and the h out in front, and I'm going to integrate this from r equals 0 to big R. But I'm going to get 2 pi rho h out in front, and I have the integral of r cubed dr from 0 to big R, and the integral of r cubed is 1/4 r to the fourth, and then evaluated it at 0 and r gives me 2 pi rho h over 4 r to the fourth. So I is equal to 2 times pi. I'm going to go ahead and plug in rho here. We found rho to be m, and then the h is here, and then the r to the fourth is here. Now the 4 on the bottom is there, and I haven't finished with the rho. Rho was m over pi r squared h, so I'm going to put the pi r squared h down here. So you see that those two parts in parentheses really are the rho. So this pi is going to cancel out with this pi. This r squared is going to cancel out with that exponent r to the fourth and make it just r squared. And then this h is going to cancel out with this h. And this 2 over 4 is going to become 1 half. And the formula I get is 1 half mr squared is equal to I. And that's the right answer, which you can see also in the table. Anybody have any questions on that? All right, so let me, uh, well, we don't have a huge amount of time. Let's go ahead and take a 5 minute break. Come back at 7:15. I'll be sitting here the whole time in case anybody has any questions, but go ahead and take a 5 minute break and we'll come up and finish a couple problems. So what we're looking at now is example 1010. And example 1010 says a heavy pulley, a 15 Newton force represented by Ft is applied to a cord wrapped around a pulley of mass M equals 4 kilograms and radius R0 equals 33.0 centimeters, figure 1022 below. The pulley accelerates uniformly from rest at an angular speed of from rest to an angular speed of 30.0 radians per second in 3 seconds. Assume the frictional torque is 1.10 meter newtons. I wrote Newton meters at the axle. Determine the moment of inertia of the pulley rotating about its center. So that's what we're trying to calculate. And what we're going to use here is solution summation torques is equal to I times alpha. And we're going to use torque is equal to R times F times the sine of theta, or whatever version we want to use. So first off, you can see that the lever arm vector is drawn as the R0 here, and it's clearly perpendicular to the normal force. And I'm going to call that counterclockwise rotation caused by the Ft to be a positive torque. So I'm going to use that as the positive torque, and I'm going to call the friction torque a negative. So that'll be the left-hand side. And I'm going to be able to calculate alpha using our kinematic equations as follows. So alpha is equal to omega minus omega 0 over delta t. And that's the average angular acceleration. But in this case, I'm going to assume that it's actually a constant acceleration, which is fairly reasonable. So I'm not even putting the average bar over it. But in this case, we're going to say 30.0 radians per second minus 0 radians per second over 3.00 seconds, which is clearly 10.0 radians per second every second. So we now know alpha. The summation of the torques, on the other hand, is going to be R0 times Ft minus the torque due to friction. So that's going to be, using the appropriate units, 0.330 meters. Notice I did convert it to meters. And the Ft is 15.0 newtons. And notice that the angle between them is 90 degrees. So sine of 90 would be 1. So I don't have to put that in there. And then I'm going to say all of that is minus the 1.10 Newton meter torque. So this gives me 0.33 times 1.5, which should be close to 5, 4.95. 4.950 Newton meters with one extra digit minus 1.10 Newton meter. And that gives me 3.85. zero Newton meters is the torque. And we're just asked to calculate the moment of inertia, so that's easy enough. We can say the summation of the torques is equal to I times alpha gives me 3.850 Newton meters is equal to I times 10.0 radians per second, and that gives me I is equal to 0.3850. And what we're doing is dividing by per second squared, and a Newton meter is a kilogram meter squared per second squared. So we're end up getting basically a kilogram meter squared per second squared divided by radians per second squared. You can see the meters per second canceling, or excuse me, the reciprocal second squared canceling out. The radian you can just drop off. So in fact, the answer becomes 0.3850 kilograms meters squared. Any questions on that? Now, if we thought this thing were an actual cylinder, then we might expect I to equal 1/2 mr0 squared. So let's check that and see if this seems reasonable. So I'm going to write 1/2. We know the mass is 4.00 kilograms, and we know the radius is 0.330 meters. So zero point 0.5 times 4 times 0.33 squared gives me 0.2178 kilograms meters squared. So this moment of inertia is a little bit larger than we'd expect, but that could be just because maybe, for instance, if you actually design a pulley or used a pulley, you'd see that oftentimes the pulley will have a very light, thin disc on the inner side, and then there'll be a significant weight around the outer edges, so that you distributed more mass at greater R. That could account for the moment of inertia being quite a bit bigger than the 0.2178 if it was a uniform 4 kilogram cylinder. So, any questions on that one? All right, now notice that one. That was where we had a constant 15 Newton force pulling down on it, a tension force of 15 newtons pulling down on it. Now we're going to do a similar problem. This will be example 1011. And with example 1011, it says a pulley and a bucket. Consider again the pulley in example 1010, but instead of a constant 15 Newton force being exerted on the cord, we now have a bucket of weight 15.0 newtons. The mass is, of course, 1.53 kilograms, because all you have to do is take that 15 newtons and divide by 9.8. C10 figure 23, we assume the cord has negligible mass and does not stretch or slip on the pulley. Calculate the angular acceleration A of the pulley and the linear acceleration A of the bucket. Assume the same frictional torque, 1.10 Newton meters, acts on the pulley. So this is example 10-11. So I have a circle of radius R0, and we have a force in this case, which is actually going to be a tension force. But what we have here is a mass of M equals 1.53 kilograms hanging from it. And we also have a friction force, which I'm going to choose to draw this way. I'm going to say that's a tension due to friction. And we are going to use the moment of inertia that we found in the previous problem, which is 0.385. If I remember correctly, 0.385. Yes. So I is equal to 0.385 kilograms meters squared. The torque due to friction is negative 1.10 Newton meters. And what we're going to do is draw a free body diagram for the pulley. And the free body diagram for the pulley is basically this. This is going to be a tension force T acting down, and we don't necessarily know it. It's not necessarily going to be mg because this mass mg is going to be falling, and therefore, if it was mg, it wouldn't fall. So the tension can't be mg. It's going to have to be a little different from that. But we also have acting on it a friction torque that causes negative 1.10 Newton meters tension there. So the summation of the torques is equal to I times alpha, gives us T times R0. Notice they are perpendicular. The R0 lever arm vector is perpendicular to the tension T, minus the friction torque. That's equal to I times alpha. And that's going to be equation 1. Now I'm going to draw a free body diagram. I should point this out. This is free body diagram for the pulley. Now I'm going to draw a free body diagram for the hanging mass. In this case, what we see is we have a tension T and we have a force acting downward that is mg equals 15.0 newtons. Okay. Now, what we're doing by calling the torque a negative due to friction, we're saying that rotation in a counterclockwise, or excuse me, in a clockwise direction is negative, and counterclockwise rotation is positive. So we want to have our coordinates consistent with that. Additionally, I'm going to assume that the T going down in the free body diagram for the pulley causing a positive torque will also cause a positive acceleration for the mass M that's hanging. So what I mean by that is that this axis right here pointing down is the positive y-axis. So now I'm going to take the summation of the forces in the y direction is equal to mass times acceleration in the y direction from the hanging mass diagram. And what it's going to be is mg minus t is equal to ma. And that really is the only acceleration we're dealing with. So I need not waste any time trying to call it a sub y or anything like that. Now that's equation 2. Now, because I took the time to say that mg going down was a positive direction and T pulling downward causes a positive torque, then I realized that rotation in the counterclockwise direction will be positive at the same time that A is positive. If I hadn't done that, then when I try to implement the idea that the rope is not slipping over the pulley, that has to happen through the equation A equals R times alpha. And if I hadn't done that consistent coordinate system, I might have to write something like A is equal to negative R times alpha. So, uh, without slipping, R stretching, we see that S is equal to R times theta, which means V is equal to R times omega, which means A is equal to R times alpha. So, what I mean by that is if I pull this rope down 1 inch, then a spot on the pulley is going to move counterclockwise through an arc length of 1 inch. That is S equals R times theta because the arc length is 1 inch, and then the theta would be whatever angle is appropriate to make that S equal 1 inch for the given R. Similarly, if I pull that string down 1 inch in 1 second, then the pulley is going to move through an arc length of 1 inch in 1 second. So V is equal to R times omega. And similarly, if I pull it in down 1 inch in 1 second, and then a second later I pull it down 2 inches in 1 second, then the same thing's going to happen to the arc and there to the arc length on the pulley. So again, I get A equals R times alpha. So that's going to be equation 3. So now what I can do is I can go ahead and substitute specifically the correct R. So let me get rid of this equation 3 and write it in terms of the R that we actually know. So I'm going to say S is equal to R0 times theta implies V is equal to R0 times omega, and that implies A is equal to R0 times alpha. So what I can do is call this equation 3, and I can go ahead and, for instance, solve, uh, let's take equation 1, and I'm going to replace alpha with A over R, so I get R0T minus TF is equal to I times A over R0. I can multiply through both sides by R0, and I get T R0 squared minus tau friction R0 is equal to I times A, excuse me, not alpha. Okay, I'm going to call this 1 prime. Actually, let's call this equation 4 and ignore that prime. It's just 4. Okay, now I'm going to take equation 2 and I'm going to solve for t. And what I get is t is equal to m times g minus a. So I can plug, let's call this 2 prime, plug 2 prime into 4. And what that gives me is m times g minus a times r0 squared minus tf times r0 is equal to I times A. So now what I've seen is I've managed to use equation 1, equation 2, and equation 3, and I now have an equation with only one unknown, specifically the unknown is A. So if I distribute this, I can get mgr0 squared minus ma r0 squared minus torque F R0 is equal to I times A. So I would like to get the A's on both sides. So what I'm going to do now is I'm going to write mg R0 squared minus torque due to friction times R0 is equal to I plus m R0 squared. Notice I went ahead and did some factoring out to make it a little easier. But basically, I pulled the MA R0 squared to the right hand side. That made it positive. And I had IA plus MA R0 squared. So I just factored out the common A. And finally, I get A is equal to mg R0 squared minus R0 friction due to torque, or torque due to friction, over I times M, or excuse me, I plus MR0 squared. So that is the actual expression for the acceleration. And you can actually plug in those values. We're just running out of time. But that is exactly the right result. And in fact, you could divide through by an R0 squared and it would look a little, be by an R0, and that might even make it look a little bit more reasonable. You can also find, for instance, that A is equal to R times alpha. So alpha is equal to, from A equals R times alpha, we know that alpha should be A over R0. So alpha should be mg R0 minus torque due to friction over I plus mr0 squared. So we've managed to solve everything we needed to solve. Anybody have any questions on that? Now, these other examples are pretty straightforward. That being said, there's one that's kind of helpful. Let's look at example 1012. We only got about 9 minutes left, but this should be pretty good. Example 1012 says a uniform rod of mass M and length L can pivot freely, i.e., we ignore friction, about a hinge pin attached to the case of a large machine, as in figure 1024. The rod is held horizontally, then released. At the moment of release, when you are no longer exerting a force holding it up, determine A, the angular acceleration of the rod, and B, the linear acceleration of the tip of the rod. Assume the force of gravity acts at the center of mass of the rod as shown. So our diagram is essentially this, okay? This little spot would be the center of mass of the rod. And what we're saying is this force right here acting downward is at mg, and it's obviously at a 90-degree angle. We're saying this length from here to here is L. And what we want to know is A, what is alpha? And B, what is A of the tip? And we only mean, because this is actually a little bit more complicated to try to calculate this, because this acceleration is not going to be a constant. So you'd have to do some other tricks. So we're just trying to initially study it. What we're going to do is say solution summation torques equals I times alpha. So in this case, what we get is the only torque acting on it is M, that's a capital M, sorry, mg times L over 2, that's the torque, and that's equal to the moment of inertia for a rod rotating about its end, which we already derived that earlier and got, if I remember correctly, 1/3 ml squared. That's it right there, 1/3 ml squared. So in this case, we're going to get 1/3 m L squared for I, and that means alpha is that. So we can solve for alpha. Specifically, notice that the m cancels out, the 2 cancels out, and one of these L's cancels out with that, and that gives us, in fact, alpha is equal to G over L. And that's consistent with the rules. The oops, sorry, I put 1/2 instead of 1/3. Sorry about that. Let's correct that real quick. That means a lot of stuff I canceled out didn't work. I don't know. I literally said 1/3 and then I wrote 1/2. I don't know why that happened. So 1/3. I'll just write it in blue since I screwed up last time. Anyways, what we see now is the M cancels out with the M. This L cancels out with one of those L's, and we're left with alpha is equal to this would be 2G over, or 3/2 G over L. So that is the answer for part A. And now for part B, the answer is A is equal to R times alpha. In this case, the R is L. So we're going to say A is equal to 3/2 R, or excuse me, 3/2 LG over L. R A is equal to 3/2 G. Now, this is a very common thing when the mass or when the force is acting on the center of mass of a system. That means things that are further out in rotation from the center of mass can rotate at accelerations greater than gravitational acceleration. So if you actually knock over a smokestack, say, or a tall building or a silo, the gravity acts on the center of mass of the smokestack or the silo or the tall building and tries to make it fall at a rate of 9.8 meters per second. But since A is equal to R times alpha, and you assume that the object is rigid, that means this far end is going to be going even faster, just like the water skier out beside the boat. Okay? And that's what we got here. We got an acceleration that's 3/2 G. Anybody have any questions on that? Your book does talk about the parallel axis theorem. I will tell you that you can use that parallel axis theorem on the rod, the broomstick that I worked, and you would say the moment of inertia, or excuse me, the moment of inertia I about a parallel axis. Let's just write this here. IPA, which means the moment of inertia about a parallel axis, is equal to I, the moment of inertia about the center of mass. So that's when we got the 1/12 ml squared. The moment of inertia there, 1/12 ml squared, is the moment of inertia when rotated about the center of mass. But for the parallel axis theorem, you now take the mass m and multiply it by d, the distance between the old axis and the new axis, squared. So in this case, we could say I about the end is equal to the I about the middle plus m. Now, the distance between the end and the middle was L over 2. So what we get is I about the end is equal to 1/12 ml squared. Just reminding you, that was what we got down here when we rotated about the end, was 1/12 ml squared. But now we're going to add to that plus m L squared over 4. Obviously, there's a common factor of ml squared, but now we have 1/12 plus 1/4 becomes 3/12, and 3/12 plus 1/12 is 4/12, so we get ml squared times 4 over 12, which is 1/3. So we get 1/3 ml squared. And you can see that, in fact, that's exactly the formula we got for rotating about the end. Uh, I skipped the perpendicular axis theorem. You'll have plenty of time to work with that if you take mechanics or whatever. but that's sufficient. And I haven't done anything on the example with rotational kinetic energy, so I'm just going to recommend you look at any of my old videos. But example 1015 is a good example, and another good example I think is 1016 because that one allows you to 1017. 1017 and all those are pretty good. 1018, yeah, all of that's pretty good. Uh, that's the one I was going for. The 1019 is the most important. So make sure you get 1019 and 1013 at least. I'm going to go ahead and let you guys go. I might make some more videos between now and Monday, but you guys are free to go. Chat me your first and last name. Don't forget to let me know if you're asynchronous or not. But have a good weekend and just keep an eye out on my YouTube channel. Subscribe maybe, and look to see if I post anything. Thanks for coming, everybody. I'm waiting here for the last person to leave in case anybody has any questions. So feel free to stick around if you have any. Beth or David, do y'all have any more questions? I'm thinking y'all might have already left, so check my other chat. That's it. All right, folks. Well, thanks again. Bye bye.